a big group. I'm very happy.
Yeah, it's going to be great. So everybody at home, here's how this works. Qin's going to introduce this topic and give us a primer on how this all works. If you have questions, this session is all driven by your curiosity. So if you have a question, please submit it to the Q&A. If you have questions for me, like in terms of just, like webinar related questions, feel free to put those in the chat. But if there are questions for the scientists, please put them in the Q&A and we'll get through as many as we possibly can before our time is up. So with that, Qin, would you like to tell us who you are, what you do, and why you like it, and then give us some explanation of how this all works?
Yeah, my name is Qin, and I'm a PhD candidate at the University of Calgary. I'm currently doing my 4th year, and I'm finishing up in April, ideally. And I really like to work on carbon storage because I really believe this is one of the ways that we can actually solve our environmental crisis. And it's very important for all of us to be on board on at least a couple of the same methods so that we're not all competing with one another and in the end, not making anything work at all. So today I'm really excited to introduce to you my work, and hopefully you jump on board with me or give me enough criticism that I jump off board. Either way, it's really great. And really great to have everybody here. Should I start on my little introduction talk?
I think that's awesome. Yeah, that'd be great.
Okay. So let me know, can you see my screen, everybody?
Yes.
And
now it's in
now, okay. And okay. So welcome everybody to Skype Scientist live stream. My name is Qin, pronoun is she, her, and we'll really talk about how to turn carbon dioxide into rocks today. And of course, geologists, we love jargon, we love these terms. So I like to show you what this means. What I study is called geologic carbon sequestration, which is any method that can securely store carbon dioxide in the ground in geologic formations. There are many ways to do it, but I think one of the most promising ways is to reuse the petroleum reservoirs, which is injecting carbon dioxide back into where it comes from, really. And in this very busy diagram, it sort of shows how it works in a very simplistic way. And I don't want you to be confused by reading all of this. I really just want to point out one term is called Caprock. And Caprock really is a very impermeable layer of rocks that's able to keep all the buoyant oil and gas underground, because oil and gas is very buoyant and it likes to flow up when you put it in water. So if you don't have a caprock to seal it underground, it will migrate up, and in the end, it will come to the surface and contaminate our water and everything. So this caprock is what's really keeping everything down underground for millions of years or even longer. And the importance of this caprock is that if it can keep the oil and gas underground, then maybe it can also keep the carbon dioxide underground safely for millions of years. And that's really what we need to reuse all of these structures. And once we inject carbon dioxide underground, there are 4 ways essentially for it to be stored over there. And I'm only going to talk about one thing, which is mineral formation reaction. This means carbon dioxide will react with minerals near it to form new minerals. And the term, of course, we come back to terms again, is called carbon mineralization. It's also called mineral carbonation. These are sort of interchangeable. And it literally means turning carbon dioxide into minerals or into rocks. And how does this work? It's chemistry. I know some people hate it, but bear with me, it's really, really simple. First, carbon dioxide needs to react with water and form carbonic acid, which is this thing. It's a very weak acid. Consider your Coke is filled with carbonic acid. So it's not dangerous, not scary. And carbonic acid isn't very stable in the subsurface. So it likes to dissociate and form bicarbonate, which is an anion. It's HCO3 minus. At the same time, carbonic acid also likes to dissolve minerals and form metal cations such as calcium, magnesium, and iron. And I like to remind you, although this is a difficult time, there's always something positive in your life at any point. All cations are positive. Jokes apart, now that we have a soup in the subsurface that contains anions and cations, what are they going to do? They're going to react with one another and form something that's stable. So this is what we call a carbonate mineral, and the S means it's a solid. So now that we turn carbon dioxide, which is a gas, into something that's a solid, it's a mineral. So this is called mineralization. And my PhD thesis really focused on use a mineral called Glauconite, it's also called greensand, to capture carbon dioxide and secure it in the mineral structure. And on the left-hand side, this big cliff in the middle, there's a lot of greenish sandy stuff. This is what Glauconite looks like. And Glauconite gets its name greensand because of its color, of course, and this green color is given by iron in its structure. So by definition, if Glauconite dissolves, it's going to release a lot of iron because it just has so much iron. And what we proved in my study is that this really happens, and it happens a lot. In the subsurface, we see on the right-hand side, this is an SEM image. So how to picture this is kind of like a very, very strong microscope, but instead of seeing light, you're using X-ray to look at the minerals. So the color is false. It is assigned by the computer, but it is telling us this big fluffy thing is a grain of glauconite. And these little squares are FeCO3, which we also call siderite. So this proves that this concept works. Glauconite does turn into carbonate when it's reacting with carbon dioxide. And so once we know if something that works, we really need to know how well it works. And here are a couple of things I encountered during my study. Well, first of all, glauconite is really, really abundant worldwide. This is a map that's probably hard to read, but it really just tells us these people found glauconite almost on every continent of the world. So this means a lot of countries have the opportunity to use glauconite to store their carbon dioxide. And to inject carbon dioxide into depleted oil and gas reservoirs means it's pretty safe and a lot cheaper because we can reuse a lot of the infrastructure and also monitoring sites. And also we have our friend Caprock to keep it in place. And also to reuse these sites, it means that workers can stay where they are. They don't need to really be retrained or relocated. They don't necessarily have to lose their job and find some new jobs. And also glauconite is really exciting because it's very abundant. I don't have global data, but from Alberta alone, I calculated that we can mineralize over 150 billion metric tons of carbon dioxide. And put this into perspective, it is about 4 to 5 times of our global emission using the 2020 data. So this is huge. And this is just one province in Canada. I really think the global potential is gigantic. But the cons, of course, because glauconite is clay mineral and it reacts really, really slowly with carbon dioxide. So it's estimated to take hundreds to thousands of years for this reaction to happen. So of course, this gives us a lot of trouble because it's not very pretty. It's not very exciting to show to the media, so we don't get a lot of media coverage. And people don't really like the idea of having a lot of carbonic acid underground for thousands of years. So the social acceptance is definitely an issue. And this is something we're working on. We're trying to improve this technology. Maybe it won't take that long, or maybe we'll find a way to really secure and make the public feel safe about it. And before I take any questions, I'd like to acknowledge that this work is done at the University of Calgary, which is the traditional territory of these people listed below. And I can take any questions from here.
Awesome. That was super cool. So effectively what you're saying, you've got carbon dioxide in the air, and then you can sort of put that carbon dioxide into water like we do with Coke or seltzer or what have you, and then pump it down into areas that specifically have that glauconite, that specific rock. Okay. So given how quickly we're putting CO2 into the air from fossil fuels, like how does you said that this process is relatively slow. So how does the absorption of that CO2 compare to the amount that we're pumping out?
Yeah, so this is a great question. And a lot of my reviewers are actually mad at me for saying this. This is no problem, because we have other mechanisms to trap carbon dioxide. For example, if we pump everything underground and then it gets sealed by the caprock, it's called physical trapping. So it can be just trapped as carbonic acid or supercritical CO2, just stays there. It will not come up. And then as long as we don't leak it back to the atmosphere, we don't really care what it's doing. So maybe it will react in 100 years, maybe it will react in 1,000 years. We don't really care, it will not bother us. And there's a lot of monitoring and modeling we can do to see if this is actually secure. But again, we really rely on this caprock. If this thing leaks, then that is problematic. So there's a lot of geophysics that goes into this to make sure this is secure.
Very cool. So in a given space that you're pumping this liquid into, like how much more concentrated is the carbon dioxide than the same volume, like the same amount of space in the atmosphere? Are we just like taking a chunk of atmosphere and tossing it down below, or are we like super concentrating?
Yeah, what we want to do is to pump this thing called supercritical CO2. So we really squeeze it and heat it up, so that it turns into this thing that's still a gas. CO2 is a gas, but it acts as a fluid. So if you picture how much water molecule you can put into a jar versus how much carbon dioxide molecule you can put in a jar, this is a lot more concentrated.
Awesome. Okay, cool. So we've got a couple questions that are kind of circling around the same question. Like we've heard that fracking can lead to earthquakes by pumping things down and that sort of thing. Is there any concern that pumping this liquid down below would cause any earthquakes, or if it's like fizzy and high pressure, like cracks or anything like that?
Yeah, so this isn't really what I study, but I read from a recently published article that it's actually not a risk, it's actually stabilizing the field, because depleted, we're talking about not making new reservoirs, we're talking about using old reservoirs, so they have been fractured already.
Right.
And so there are cracks that we can just already use, and by filling these cracks, it's actually stabilizing the subsurface. So I don't know how well received that paper is, but by pumping carbon dioxide into the ground, it actually reduces earthquake risks.
That's awesome. That's super cool. Okay. So Are there, this is from Mrs. Osmond's class, are there any environmental implications to burying carbonic acid? Like, do we have to worry about drinking water in the area or anything like that?
Yeah, so this is another major issue that we really need to consider the caprocks, because our oil and gas reservoirs tend to be about like a couple thousand meters down from the surface, and our drinking water is typically way up here, a couple hundred meters below the surface, or even like tens of meters under the surface. So as long as the caprock doesn't leak, we really don't contaminate everything above. We are not talking about the same rock layers at this stage. But of course, everything could go wrong, and we really need to consider the site selection. So we probably don't want to inject carbon dioxide directly under some like major reservoirs, just in case something happens.
It would what would the worst case scenario be in that situation? Just like acidic drinking water, or worse?
So you just have a lot of carbonic acid that's moving upwards and dissolving rocks along the way. And it's bad because then it can mobilize your metals. And a lot of metals are toxic to people, to plants. So if it really happens, the worst case scenario is that we contaminate a huge area. So this is something, you know, the oil companies are already really good at, because they don't want their oils to move up and contaminate everything.
Right.
And if we can just like work with them and then figure out if this actually is very secure, then yeah, we can make sure this doesn't happen.
So over time, so I'm thinking, you know, in the short term, when humans are living in these areas, we can kind of monitor the situation.
Yes.
But is the idea that over like more geologic time, like evolutionary time, do we have to worry about the, like after humans are dead or maybe no longer live there, like it later seeping up and then killing whatever animals live there then? Or will the process of the carbon dioxide glauconite reaction, that rock reaction, like neutralize it?
I think while in the end neutralize it, not necessarily just glauconite, sorry, not necessarily just glauconite, but it could be anything else in these rock layers. It can all react with acid. So it really, if we can just securely keep this amount of carbon dioxide underground and then monitor for a couple hundred years, I think we're pretty sure it's going to be safe. It's not really going to kill everybody in the area. Yeah, but we're still talking about a long commitment.
Long time, multiple generations of humans. Long.
Yes, definitely.
Oh boy. All right. Sounds good. The next question's from Sarah, not this Sarah, a different Sarah. How far down are the cap rocks that physically trap the carbon dioxide?
So cap rocks can be anywhere as long as it's above the reservoir itself. So in carbon storage, we like to inject everything under 800 meters, so 800 meters and below, because that is when we can turn carbon dioxide into its supercritical form. So we want the caprock to be anywhere just above that. It will be fine.
Cool. All right, the next question is from Kylie. Like, how did you learn about all this? How did you get all this information to be the expert that you are today?
Well, a lot of reading. I think last year I finally did a calculation on how many papers I've read. So within the year of 2021, I read 114 scientific papers. So really read what others do. And then, of course, my advisor and my colleagues helped me a lot. And yeah, really just be passionate and love what you learn, so that it's not a tiring job. I never felt really fed up or annoyed by my job. It's really fun for me.
Awesome. Sounds good. Let's see. this is from Gavin. Is the caprock already in the earth already? Like it's existed before we dug down, or is it a man-made like cap?
Yeah, so maybe it's easier to show you different slides here. So I made this for another talk, and this is really 4 types of oil traps. Are you seeing my screen? Sorry.
I can see it. We all good. All good.
Okay, good. So oil and gas traps, they are naturally formed, and this is to have these formations are the only ways you can ever have oil and gas to begin with. If these don't occur, then you never have oil in the first place, then we don't even have this problem of carbon dioxide to solve. So what happens is that when oil forms, it is very buoyant and it likes to move up. And you need to have some structure on top of it. Like in this case, it's the layer A. Just notice every structure has a layer A. If you don't have this, the oil and gas will just keep moving up and seep through the earth. And this happens a lot, and it really doesn't cause a lot of like catastrophic events because it happens so slowly over time. And we just wouldn't even have an oil reservoir in the first place. This is not even a problem. So the only way to have oil reservoir is to have this layer A, the caprock, which means if we want to reuse any of these reservoirs, they're already in place and they're already intact for millions of years when the oil has been trapped in there. So you can imagine it being pretty secure, pretty robust.
Cool. That makes total sense. Sounds good. We have a question from Will. Where do you find green sand? Like where in the world would you go to find like a green beach, for example?
I think, so these people did a survey. I don't really know if it's very easy to see. So in general, green sands likes to form in places that is kind of warm with lower tidal activity, so it's not very strong current. So shallow marine, and wherever there is shallow marine, if you dig really deep into the earth, you will find some glauconite. It's very likely it's there. And these people did a survey that is not complete, but you can see it's mainly distributed in kind of the warmer climate of the earth. But of course, if you look at Canada, we have a lot of the really old glauconite. So it's not currently being formed or recently formed, but it's ancient and it's got preserved. And that's why they are underneath the earth and in those oil reservoirs, buried thousands of meters below the ground.
Awesome. That's super cool. I know there are definitely some green beaches, but I don't remember where they are. Anyway, the next question is from Caitlin. How exactly do you know when to put more carbon dioxide in? Like, do you have some sort of like pH meter to be like, okay, that well is good to go. Let's seal it off and be done pumping CO2 down there?
So I think there isn't a really good way to monitor that right now because we haven't been able to actually do anything in the industrialized scale. And everything we're doing right now is almost experimental scale. So nothing is at saturation. Everything has a lot more capacity to take more carbon dioxide. And what we really need to do is to start injecting. And then that's when we can know when to stop and what's the best capacity we can get to. Right now, all of the estimates are really, really conservative.
Right. Cool. Sounds good. Also, Carmen in the chat just mentioned that on the Big Island in Hawaii, there are green beaches, but it's due to a different rock called olivine and not.
Olivine, yes.
Yeah, right. Okay. Thank you, Carmen. I know. So I've done field work in Hawaii. I'm like, I know about green beaches. Anyway, but you're right. It's from that. Thank you for contributing that. The next question is from Courtney. Are there other gases that caprock can absorb? We know there are other greenhouse gases that we're worried about, like methane or something like that.
So there are a lot of talks nowadays to sort of co-inject carbon dioxide with something else. I think sulfuric acid type of gas is often produced with carbon dioxide if you're burning coal. So that makes this injecting fluid really, really acidic, and it's very corrosive to the caprock. So I think that's one of the concerns, that if we co-inject all of these other things, can it still be secure? And I think a lot of studies still need to be done, and I know people are working on these things. It's just not what I'm studying right now.
Right. Cool. Sounds good. The next question is from Will. If we're taking CO2 out of the air, will this be a problem for plants and trees that need CO2 to breathe?
I think we have so much carbon dioxide that this wouldn't be a problem anytime soon.
Yeah.
To go back to pre-industrial level, I think we need to remove about 150 ppm of carbon dioxide, and that's a lot. If we just, I think right now there are maybe 20 injection sites that are currently running in the world. And to meet our goal that's set by IPCC to increase the global temperature by 1.5 degrees, these industries have to be scaled up by another 1,000-fold.
Oh
so
my God.
That is a lot. And some conservative estimate would say 10,000-fold. It's really, we are so far behind that we don't need to worry about trees and plants yet.
So, okay. So, let's say we do that. Let's say we open 10,000 facilities for this, but it takes 300 years or what have you to get all of that. To get it absorbed by the rock, but not to just like get it out of the air. We could get it out of the air.
To just pump it into the ground. It doesn't take much time.
And that would be
like,
now we've prevented the climate change, and we'll just let it kind of do its thing and hope that we don't accidentally poison the earth above it in the meantime.
Yeah, so that will be a very different industry than what we're doing today. It's basically creating a really big landfill, right?
What a catch-22. We've really gotten ourselves into it. Okay, the next question is from Mrs. Osman's class. How quick is the process of completing your PhD research to applying it to industry to actively use what you learned?
So I'm planning to finish my PhD this year, which will be exactly 4 years. And the industry, I think there's something out there to do, but I think there's still a lot more unknowns. So I'm not really trying to go to industry right now. I think there are a lot of startups that have really, really exciting opportunities to do something similar to what I'm doing, but we need a really large scale industry for something like this to work. We need to keep everybody on board, the government, the oil companies, really any investors to be on board. So I don't think the industry is really there, but I think in the next decade or so, it will be a really, really exciting field.
Awesome. That is super cool. We've got a question I was wondering too from Gordon. If you use fossil fuel power machines that pump all of this down, is it going to be like creating CO2 as you're pumping CO2, or is the scale of like grabbing CO2 versus using CO2 to power the whole thing, like just at different scales?
So this is, I don't have a number for this, but actually pumping CO2 back into the ground is something that oil industry already does. And they can do it rather effectively, and which means they will make a profit in this process, which means, you're not using more energy than you create.
Right.
And I think if we can scale this up, it will get even more efficient, because everything gets more efficient if it's industrialized.
Right.
So I believe it will be a net negative in terms of emission, and very, very large difference will be made.
Sounds good. Yeah, that's good. Good to hear. We've got a question from Barrows STEM Academy. Would taking gas out of the air affect the atmospheric pressure that exists at all?
So this is an industry called direct air capture. And what they do is essentially they build a lot of big fans and then they pump air through it. And then in these fans, I think they use some sort of catalyst to capture the carbon dioxide and leaves everything else out of it. And because it's not a very fast process, it's not really like putting a vacuum in the air and suck everything away. The atmosphere will equilibrate over time, really way faster than we capture it. So really it's not going to make a global change. It will probably affect the atmospheric concentration of gases in the local scale, but globally, it will not make a big effect.
Sounds good. The next question is, how long did it take you personally to become a scientist like you are today? This is a question from Gabe.
I think really about, I would call it 5 years. I didn't really know what I was trying to do in earth science. After undergrad, I got a geology degree because I just love minerals and didn't really know what to do with it. And then during my master's, I really found out this thing about carbon storage and that it's something I can actually do. It's something that requires a lot of work still and requires a lot of work to happen quickly. So yeah, it's all what matters is to find, where you're needed.
Yeah, for sure. Sounds good. So the next question is from Aparna. How did researchers find and map all of the glauconite sites around the world? Like, what's the process for finding all of this rock?
I think for this one that I'm showing right now is really, they are just finding it on literature, and then some scientists are going to the site to confirm it, and some are really just because people recorded before and they put it on their map. So it's a lot of collaboration with people from before and people all over the world. And all of these kind of mineral budgeting is very difficult to do because a lot of us don't necessarily share our information, and some things are just lost in communication. So I would call this really good publication, but it's definitely incomplete because we simply can't have everything.
Right. Yeah. It would be better if scientists more effectively communicated with each other, but
yes,
we're
trying
a pretty good job. But usually after we've answered the question that we're trying to answer, then we talk to each other. But before, we tend to not do that, which it's all about competition, which is a darn shame. The next question is from Joe. Did you always want to be a scientist from when you were little?
I wanted to be a stage artist when I was little.
Yeah.
I wanted to do makeup and lightings and all that, just always about theater. But yeah, somehow got into science through makeup because there's minerals in your eyeshadows. And then I realized, there's a lot bigger stage out there that is more exciting.
That's awesome. All right, the next question is all about how do we get from the carbon dioxide being in the air to the liquid form? How do you even get it out of the air in the first place?
So one of the ways to do it is called direct air capture, is what I just talked about, the big fans and catalysts and all that. That's very expensive. I think there isn't a really industrialized site that's doing it currently. As far as I know, maybe there is. But and another way is actually a lot cheaper, is to directly capture it from for example, your coal burning plant, your in big factories where they are producing the carbon dioxide, and you put a cap on those factories and use the same catalyst to filter out the carbon dioxide, and just squeeze it really hard, make it into a liquid, and transport it into the site where you inject it. That's a lot cheaper. And actually, we're doing that right now. For example, our sodas, is using carbon dioxide and enhanced oil recovery. That's also injecting carbon dioxide into the ground. So it's not new or dangerous by any means.
Gotcha. That's really cool. So you're kind of like putting a sock on it before it goes into the atmosphere in the first place. That's great.
Yes, yes.
The next question is from Carmen. How expensive is this whole process?
This is something that's really, really out of my depth. I don't know how to evaluate how the cost and all that. But I can tell you it's probably cheaper than a lot of other methods because we don't need to build new pipelines and infrastructure, and a lot of the practice is the same as what we have been doing. So I think it's a lot cheaper than, for example, injecting it into the ocean floor or using olivine, which is the other green sand. So there's another talk to, they want to spread olivine all over the world. I think that would be very expensive because first of all, you have to mine the olivine and then crush it and then spread it everywhere. Right. So, and the olivine is also a gemstone. So you're gonna drive the price up for sure. Right. People will not be very happy about that. So I think this is probably the cheapest method we can find so far.
Sounds good. Fair enough. The next question is from the American International School of Lagos. Will this process make it dangerous to search for oil in the future?
I don't think it will be dangerous. Well, one thing I didn't really mention is that on top of our climate crisis, we also have an oil crisis. And it is predicted that we'll reach peak oil in 2050, which means we'll use up most of the oil in a couple decades. And I don't think, because oil is not renewable and we have a really good understanding of where they are because there's a lot of money in it. People really, really studied where the oil and natural gas and everything, where they are. So I don't think there's a lot of opportunity to find a lot more petroleum resources. So I wouldn't worry about that so much.
In the future, we won't even have oil to burn. We will have used it all. So
yeah, we're simply running out.
It'll all be gone, right?
Yeah.
Yes. All right. So the next question is from Courtney. Is CO2 flammable? And if too much is trapped in the earth, will it explode?
It is actually not flammable. And that's a great thing about CO2. It's got so many bad reputations, but it's very, very useful. And yeah, you don't ever see, you know, kind of soda catching fire. So it's, we can compress it, we can inject it into fluid, it will not explode by burning up. And also one thing is that to have something catch on fire, you need to have oxygen. And picture 2,000 meters underground, there is no oxygen really in there. And so it is pretty much impossible to make that explode.
Make an explosion even happen. That's good. The next question is from Noah. Are there any other reasons why there are concerns about the dangers of CO2 storage, other than just like it leaking out of the capstone and causing issues?
I think also our environmental or social justice, because a lot of oil fields and like injecting sites are actually in the indigenous land, and also pipelines go through their land. So if we're going to just extract all the oil and leave them alone, maybe that's what we're doing right now, and it just feels better than, you know, coming back to the same land and then putting more stuff into it and then having to monitor it for hundreds of years. I think it's really not very acceptable for a lot of those societies. But if we turn this around, it could create a lot of job opportunities. So if people can work together, I think there is a solution. But really, we need to all work together.
Sounds good. All right, so we try to wrap these up right around 45 after. So we like to ask everybody the same two questions before we let you go at the end of these sessions. One is, if you had everyone's attention in the whole entire world and you could tell them one thing about your area of expertise, what would that be?
One thing I want to say is that we're ready to do it now, today. We can do it. It's not some futuristic sci-fi type of thing. We know everything, every part. We just need to do it. And this involves a lot of different parts to work together, your government, your founders, your oil industry, and of course, scientists, engineers. So, but if we can get this started, maybe we can actually reach our goal of limiting to 1.5 degrees by 2050.
That's awesome. That's really, well, that's heartening to hear. I feel like it's mostly doom and gloom on the climate news. That's good to hear. That's great. Okay, that is gonna give me a hope for the rest of my week. The next question is, you still have everybody's attention in the world, and you can tell them one thing about anything. It can be as big picture, important, significant, or silly, and just something that you like. It's up to you. What would you tell them?
Well, this really catches me off guard, but right now I want to tell everybody, get vaccinated, wear your mask, and stay safe. I hope everybody gets through this, and then we can solve global warming together.
Yes, I hope it's almost over. Knock on wood. All right, thank you so much, everybody. Thank you for joining us today. I'm really glad y'all had the chance to be here. Our next session is going to be on January 28th. That's a Friday. We're going to be talking all about conservation with Al Troutman. Al is an incredibly engaging, wonderful scientist who works on marine ecosystems and a bunch of other stuff, and is just the coolest. So hope to see you there. I put the link in the chat for everybody to check out. If you want to share this with somebody after having watched it, you can go to youtube.com/Skype-a-scientist, and all of our videos are always posted there. Qin, thank you so much for sharing all this super cool cutting edge knowledge with us. I feel like we don't hear enough about the details of carbon recapture. We just like hear hand wavy, like maybe we could do carbon recapture. So I learned so much today. And Ashley, thank you for interpreting for us. And everybody, we'll see you soon. Is there anything else you'd like to share, Qin, before we say goodbye?
No, thank you for having me, and thank you everybody for joining us. It's great to talk to all of you.
Yes, awesome. Okay, we'll see y'all next time. Goodbye.
Bye-bye.